Okay, thank you. Can you hear me? Okay, thank you very much. Thank you for the organizers for the invitation to give the talk, and especially for putting this cost action into action. And thank you everyone else for staying here despite your empty stomachs. So this might be hard, but I will do my best to capture your attention. And I guess that since we will have a Spanish lunch, like at a late time, what could be best than having a Spanish speaker to entertain you meanwhile? And since we had this beautiful path, this road through this botanical garden, what could be best than following this road towards precision swampland? So what I'm planning to do, I'm going to focus on one concrete idea of the swampland and some of these developments that try to make this much more precise and get some useful phenomenological constraints. But first of all, since this is supposed to be a vision talk and it's supposed to be aimed, what we were saying, like for a PhD student that is in your institution but maybe not in your group, that was the instruction. Let me briefly remind you what is the goal of the program and what we are trying to do. So the question we are trying to answer is, what is the space of effective field theories that are weakly coupled to Einstein gravity and can be consistently UV completed? Okay? So the message is that if you have some effective field theory coupled to gravity and you have a bunch of higher derivative corrections, not everything that you put here necessarily is guaranteed to have a UV completion. Okay? I mean, this already happens in quantum field theory, but in gravity with more reason. So we try to understand what are the rules of the game. Okay? So what can go here, and also what is this cutoff? Because depending on what you put here, what we learn from string theory is that this cutoff can actually be lower than the Planck scale. Okay, so this is just my favorite picture. Well, actually, this is my favorite picture. So the idea is that not everything can be UV completed. So the theories that arise from some quantum gravity description at higher energies belong to the landscape, and the ones that are not consistent belong to the swampland. Okay? So the swampland are those that cannot be UV completed. Okay, so the goal is to understand what are these constraints, what distinguishes this beautiful landscape from this ugly swampland. And by doing that, I mean, of course, that's interesting by itself because it's like uncovering what are these quantum gravity rules, no? These principles. But the hope is that they can also bring a new way to connect with our universe by providing guiding principles to construct beyond standard models, particle physics and cosmology, and hopefully shed some light also in some naturalness issues, because gravity is different than the other interactions and can induce some UV-IR mixing. So the take-home message is that even if the Planck scale is very high, working in quantum gravity is not just a mere theoretical exercise. It can have implications and can impose non-trivial constraints at low energies. Now, how useful are these particular constraints for our universe is yet to be seen. That's what we are working on. But we have proof of principles that they exist. Like there are at least some constraints. Then you can see it's more or less useful for the universe, but not everything goes. Okay? Not everything is consistent. So we have some proposals for these constraints. They go typically under the name of Swampland conjectures because they are motivated by what we know from string theory and arguments of black hole physics. But formulating the conjecture is just the first step. Okay? So the way we work is that, okay, you identify some pattern using all the data that has been collected in all these years of learning about string theory. And then you have to work harder. You have to provide quantitative evidence in string theory. So this is a fantastic theoretical framework to test it. And then if you want to understand, you want to distinguish model-dependent features from universal ones, you need to understand why these constraints should be true. Like, what goes wrong if you don't satisfy it? You can try to do it thinking of black hole physics. You can try to prove it using IDS-CFT, for instance, maybe scattering amplitudes, and so forth. Okay? And then you can think of the phenomenological implications. So this is this road towards precision swampland that we are pursuing. So there has already been several years that there has been this growth of activity in this program. So what has been the history so far? So there were some constraints like proposed years ago, which are like the core of the Swampland program. Then probably you saw in the archive many more constraints arising at the beginning. After that, what happened is that we started to realize that all these constraints are different phases of the same principle. They are actually related. So right now, there are like three groups, like three basic constraints, which are some of them are related to the absence of global symmetries. Others put constraint on the field spectra and constraints on the scalar potential and the landscape of flash vacua. And now what we are entering is in what I call like an era of precision, mimicking cosmology, in the sense that we are really making very precise all these constraints and even giving proofs in certain setups. Okay? So in order to exemplify this, I'm not going to go through all this. I'm going to focus on one. Okay? We want to focus on one idea. So I'm going to focus on this distance conjecture. Why? Well, first, because it plays a central role in the Swampland program because of many of the connections. It's also one of the most natural features from string theory. Like if I had to pick one, I would actually pick this one. You will see why. But it also has phenomenological implications. So it's a bit of a sweet spot between getting something that seems to be universal in string theory, but can have an impact. So, and it's also a very good example to understand how it has changed a lot, our understanding of this conjecture in recent years. So there has been a lot of work sharpening the conjecture, getting rid of all the ambiguities, fixing all these order one factors, everything, and even trying to provide proofs that are model independent, for instance, in the context of ADS-CFT. So what I want to do is mainly to focus on this part of ADS-CFT. Okay? Very good. So let me start by summarizing, like reviewing what this conjecture is about. So the idea is that if you have an effective field theory that is weakly coupled to Einstein gravity with some field space that is parameterized by the vacuum expectation values of the different scalar fields. Okay, so you have a theory, different scalars. That happens very often, right? In string compactifications, we get a lot of scalars parameterizing the internal dimensions. But okay, more generally, you get these scalars, and you can define some field space, so such that the metric is the field metric of the kinetic term of these scalars. Okay. What the distance conjecture says is that there should be a new physics, an infinite tower of states that become exponentially light when approaching an infinite distance boundary of this field space measured by this metric. Okay? So, what do I mean? So if you think of this field space, so each point is a different value for the scalar wave. And you approach some of these boundaries of the field space, you should get this tower of states that become light. And all of them become light. Okay? So you had infinite new degrees of freedom at the boundary. Okay? Good. Now, this happens all the time in string compactifications. For instance, if this scalar happens to parameterize the volume of some circle or some internal space, if you make it very large and go to infinite distance, you are going to get the Kaluza-Klein tower becoming light. That also happens if you go the other way around, like to make them small. That's also at infinite distance in this metric. And then you get winding modes, wrapping brains, and so on. Also, like couplings, like you get the string coupling. You send it to 0, it's at infinite distance, you get the string modes. Okay? So the point is that from the perspective of the effective field theory, getting this infinite tower of states implies a drastic breakdown. Okay? Like you get this new, I mean, you cannot have a quantum field theory description anymore because you have this infinite tower. And then the scale at which quantum gravity becomes important becomes parametrically below the Planck scale, okay? Because they are all becoming massless. Okay? So with this tower, you get also that the cutoff goes to 0. in these examples, like for instance, like you have the string tower, then I'm talking about the string scale. If I have a Kaluza-Klein tower, I'm talking about the Planck scale of the higher dimensional theory, and so on and so forth. Okay? So if you are interested, if you work in particle physics and cosmology, and you have some effective field theory, and you wonder what is the scale at which quantum gravity should matter, it's not true that that's always the Planck scale. In fact, that can happen in the middle of the moduli space, but as you approach these boundaries, this scale is always much lower. Okay? That's what we observe from string theory. So what is this useful for? Well, first of all, it puts a bound on the scalar field range, because I mean, if you are moving in this field space, at some point you find the tower. So this is the maximum field range, the geodesic field range, that you can describe for an effective field theory with a fixed cutoff. But you can go beyond that, because like in general, when we have the effective field theory, all the couplings and masses are parameterized by vacuum expectation values of the scalar fields. So you can also put bounds not only on the value of the scalar fields, but directly on the value of the parameters of the EFT. For example, if you take a weak coupling limit, like a gauge coupling goes to 0, it becomes very small, or you try to engineer some approximate global symmetry, these limits are at infinite distance in this field space. Okay? So that means that whenever you try, for instance, to have a very small value of the gauge coupling, you are going to find these towers of states becoming light. And then you can use it to put a bound on how small the gauge couplings can be. Okay? That's kind of the idea. And that's what we are trying to quantify, okay? Exactly how this behaves. And then, as I said, like, then you can use it to construct models of like weakly coupled, dark matter, dark photons, things like that. Okay, so as I said, like this is, I mean, the existence of these towers is kind of one of the most universal features of string theory. You always get these towers when you go to the boundaries. They are behind all these famous string dualities that we know and love. It's very natural. It's not surprising from the perspective of string theory. Sometimes it's like, okay, why you even talk about this? I know this happens all the time. But the key point is that even if it's very natural for string theory, it's very surprising from an EFT perspective. Because you are telling, for instance, that if you have a quantum field theory with a perturbative weak gauge theory, like the gauge coupling is very small, something has to go wrong because you are getting too close to these boundaries and you get this tower of states. And that's something that will never happen in quantum field theory. It's rather the opposite. Like the smaller the gauge coupling, the more control we have of the theory, right? So quantum gravity is changing this, okay? And that's a message that matters when you work for phenomenology, no? Like, and you try to make these couplings very small. You have to be careful that they are not too small to make the quantum gravity cutoff to go down. Okay? Now, so that's the observation. So what do we like? What we want to do? Well, first, we want to understand why. Like, okay, this is what you observe in many examples, but why do we always get these towers? Can we uncover the quantum gravity principle behind the existence of these towers? Why it has to be wrong? No? And second, we want to make it more precise. We want to understand what is the possible nature of the towers and what is the value of the exponential rate. So exactly how fast they become light in order to be able to give a quantitative prediction for phenomenology. Like, so far it's just qualitative, like they become light, but if you cannot tell exactly how, you cannot give any useful constraint, okay? So as I said, like the first step was just to identify the pattern, but then, since then, you have to be able to answer these questions. And there has been a lot of activity trying to sharpen this conjecture, understanding the value of the exponential rate and all these things from the perspective of string theory compactifications, but also there has been recent progress on trying to understand, using black holes and ADS-CFT, why the towers are there. Okay? So what I'm going to do is just, I'm going to give you one slide to summarize what is the state of the art here, what are the values of the exponential rate, and then I will spend the rest of the time in the, like, explaining how this works in ADS-CFT. Okay? Good. So, one slide. So, yeah, there has been many, many papers. I mean, it's impossible to put all the references, but basically, even if you take, the conclusion is that doesn't matter what infinite distance limit you can take very complicated internal manifolds where you have many, many scalars, go to very different regimes, strongly coupled, weakly coupled, whatever. In the end, you can always find a change of dualities such that the tower of states looks like a Kaluza-Klein tower in some dual frame or some string tower, like oscillator modes of the string. So in the end, it's like coming from string theory, no? Like either the extra dimensions or the perturbative string. Not like wrapping brains, they are never like the leading tower. Okay? So, and then, even more importantly, like the nature of the tower, the microscopic nature of the tower, fixes completely the value of the exponential rate. So depending on what is the nature, you are going to have that the exponential rate is given by 1 over the square root of d minus 2, where d is the dimension of the space-time. If it's a string, the critical string, or this is, for example, the case in which you just have compactification, in which warping effects are not very important, otherwise this gets modified. Okay? But the basic point is that there is a one-to-one correspondence between this value of the exponential rate and the nature of the tower. And since the Kaluza-Klein tower seems to always decay faster than the string, because it's more dense, there is a sharp bound on the value of the exponential rate, which is what you need to give a bound on the field range. Okay? So this is the state of the art right now. And what I want to do the rest of the talk is to understand how, if so, this gets modified in ADS, and whether we can prove this using CFT. Okay? So it's not just a matter of checking example, but we have a general proof of this conjecture. And well, you will see that actually this has to be modified because we can have more types of tensionless strings. We'll see. Okay, so how do we translate this constraint to ADS-CFT? Well, let's start with the easiest example in which we really have a moduli space. So all the scalars are massless. And this translates, moving in this moduli space is equivalent to moving in the conformal manifold of the CFT, which is the space of exactly marginal couplings. The field metric of the kinetic term that we use to measure the distance maps to the Samolov-Hikov metric in the CFT, which is given by the 2-point function of the marginal operators. And then this tower of light states are going to correspond to tower of operators that are close to saturate the unitarity bound. So the distance conjecture translates to the statement that there should be an infinite tower of operators saturating the unitarity bound at every infinite distance limit in the Samolov-Hikov metric, such that the anomalous conformal dimension decays exponentially in terms of the distance measured by this metric. Okay? Good. So, does this happen? And if so, what are the towers? What is the microscopic nature of this tower of operators? Well, the answer depends on what dimension you are. So this is something interesting in ADS-CFT. It seems to happen that if you are in two-dimensional CFTs, all the examples that are known and has been conjectured that is the only option is that you have the scalar gap going to 0. So you have like tower of scalar modes that in the bulk correspond to tower of Kaluza-Klein states and so on, like partial decompactification. While in dimension bigger or equal than 3, all these towers always correspond to higher spin modes. Okay? So like string states in the bulk. And this is what we call the CFT distance conjecture, okay? Including this separation between this nature of the tower. Now, if you want to prove this, okay, that this always happens, you need to show this one-to-one correspondence between the infinite distance and the infinite tower. This is supported in all the examples in holography, but recently, after we've put this conjecture, like just in these 2 years, there are already 2 papers proving this direction of the arrow, so that once you have either the higher spin gap in higher dimensions or the scalar gap going to 0 in 2 dimensions, this point must be at infinite distance in field space. And now there is work also trying to prove the other one. So this is one example in which this constraint is not out of reach to try to give a rigorous proof. And actually, the techniques employed here are not like new techniques that we had to develop. It's just using known techniques to address the question that is interesting for us here. Okay? So I hope this also encourages try more using your own techniques to prove some of these statements. Okay, so how much time do I have? 20 minutes? 5, 7? 5 minutes. Okay, so in the last 5 minutes, let me focus on the case of the higher spin modes and give you a bit more details of why they appear, or like how this is working. And also to, as I said, like to sharpen, to understand how light, what is the exact rate at which they become light, and what can we learn from it. Okay? So, very quickly, so let me focus on dimension bigger than 2. The only conformal manifolds that are non-compact, that are known in CFTs, occur in 4 dimensions. Okay? Although there is this proposal in 3 dimensions that would be nice to study more. But let me, for the moment, focus in these 4-dimensional superconformal field theories to explain you a little bit like what is the intuition of how you get this tower of operators of higher spin modes. So in all these examples, the infinite distance limits are weak coupling limits in the CFT. So you have some gauge coupling from your CFT that goes to 0, which means that at the boundary, at the infinite distance limit, you get this, like a part of the theory becomes free. Okay? And now you can see what's going on. Once you get a free point, a free sector, by Maldacena-Sivoedov, this automatically implies that you have a higher spin symmetry. Okay, so there is a one-to-one correspondence between having these weak coupling limits and a tower of higher spin operators saturating the unitarity bound. But okay, to prove the distance conjecture is not enough to show the existence of the tower. You need to show that they decay exponentially. So you can do that. You can say, okay, if you take the free limit, the gauge coupling goes to 0. You know that by perturbation theory, the marginal operator is just the trace of f squared. You can compute what is the Samologikov metric. And it always takes this hyperbolic form, such that in the end, the anomalous conformal dimension behaves exponentially in terms of the distance. And you can compute explicitly what is the exponential rate, like how fast it goes to 0. So this implies that from the perspective of the ADS dual, you are going to have a tower of higher spin fields with an exponential rate, which you can compute to be the square root of 2 times the central charge over the dimension of the gauge group that is getting free. Okay, so you see that the exponential rate gives you a notion of what is the portion of the theory that gets free. Okay? And moreover, it's also like there's a lower bound, which is consistent with the lower bound that I gave you before. Okay? Okay, so one last comment is not only, this is a way to sharpen the conjecture. This is the concrete value that you have for these exponential rates. But it's not only that it's lower bounded, like the numerical values that this can have are also very constrained. So to give you one example, you can take the full classification of 4-dimensional superconformal field theories that have a simple factor for the gauge group, okay, just to simplify a bit the story, so just everything gets free, okay, you just have one factor, one gauge coupling. So these classifications were performed in these papers, and then you compute this value of the exponential rate, and you get that there are only 3 possible values that arise. That's it, for all these superconformal field theories. And they are mixed. It's not that they correspond to the different gauge groups, they get mixed, and it's not that they correspond to n equals 1 or n equals 2, they also get mixed. It's like you have a new classification of the superconformal field theories in these 3 groups. Okay? Now, you can ask, okay, why this is happening? Well, if you study this in more detail, you can see that in this case, you can write this exponential rate as a function of the ratio of A over C, the 2 central charges of the CFT. And in all these cases, it happened, I don't know if any of you knew before, I didn't know, that A over C can only have 3 values. You can show this just by because of having the CFT, okay, the conformal manifold. So, and this is what gives rise to these three values of the exponential rate. Now, I told you before that the nature of the tower completely specifies the value of the exponential rate. So now you can ask, okay, why you have three values here? Like in all these cases, they are all towers of higher spin fields. Okay, so it's like having a tensionless string limit in the bulk. So does this mean that these three values correspond to three types of tensionless strings? Like these three types of quantum gravity resolutions that we can have? And the answer, I mean, we think is yes. So this is work in collaboration with Jose Calderón Infante. We are computing, for instance, the density of the operators, like the Hagedorn spectrum at the free limit. So indeed, one can see that there is a Hagedorn growth because of having this tensionless string. But the Hagedorn temperature is different for these three cases. Okay, so they really suggest that there are three types of tensionless strings. The first one is the usual critical string. So this is like the string in n=4 superjump mills. So any holographic theory that has A over C equals to 1 to leading order, it's gonna, like the free limit always corresponds to this, our known critical string. But it seems that there are two others, which happen in non-holographic theories in the sense that even if you have a large n, you don't have a large gap. Okay, so A is different from C. And they correspond to different string worksheet descriptions that you get at infinite distance. Okay? So first thing you learn is that this distance conjecture seems to be more general than only for like weakly coupled Einstein gravity descriptions. It works for all CFTs, regardless of whether you have a large gap or not. So it's a very intrinsic feature. And second, by understanding these limits, we get information about the possible quantum gravity resolutions, no? Like what's going on at high energies, what are the string theories that appear. And since there are only these three groups, it also means that there should be a way some duality or some way to connect them among each other, okay? Like the CFTs that are in these groups. Okay, so I think this was it. I had some bonus slides, but I don't know if I have time to explain it. Let's go to the conclusion. So you can ask me later about it, okay? It was just in case I had time. It's just to show you, just so you know what's about. The idea is that if you try to understand what happens beyond the conformal manifold, so when the scalar fields get also a mass, you can actually use these values that I told you of the exponential rate to give an argument against scale separation in ADS. Okay, and to explain why you don't have scale separation. But then you can ask later. So let me conclude. So yeah, I think the message is that consistency with quantum gravity at high energies can have implications, like not everything goes. We are trying to make all these Swampland constraints more precise, giving sharp bounds on the value of the exponential rate, classifying all the possibilities, and trying to give proofs, at least within concrete setups, like ADS-CFT or classes of string compactifications. So let me finish with the message that, I mean, this is just one example. There has been also more recent papers using ADS-CFT or CFT techniques in general to prove like the good gravity conjecture or other Swampland constraints. And there is much more than can be done. Okay? So I hope this encourages everyone to use your favorite approach to quantum gravity to try to relate to some of these constraints to see if you can understand what's behind and see if we can all together uncover what is the quantum gravity constraints that are imposed at low energies. So thank you.
Thank you very much. Questions? Okay, several at the same time. Let's go.
Hi. So in the context of Minkowski vacua from Calabi-Yau compactifications, there are these so-called K points at infinite distance, which don't have, as far as I know, a good geometric understanding. Are you saying that it's
Which
still...
one? Sorry, say again?
So that is so-called K points at infinite distance, corresponding to variations of Hot structures where, where the monodromy at infinity is not maximally unipotent, so they don't correspond to large volume limit.
Yeah.
but I'm not sure it's known to what is their
Yeah.
So can you actually prove this distance conjecture in that context?
Yeah, we had a paper, like actually one of the first ones, in which we took tried to get the complex structure of a Calabi-Yau threefold, classify all possible infinite distance limits, which are classified by the the order of the infinite order monodromy, like the nilpotent orbit theorem. And then we use techniques of Mises structures to prove the existence of the tower of BP states.
But still, there is no dual frame in which there would just be your Kaluza.
Yeah, so in that case, exactly. So in that case, we can show, using the Hodge theory, we can show the existence of the tower of states. But it's an open question to understand, what is the duality, right? Like, what is the change of dualities that would show that they are Kaluza-Klein or stream Mossos? That's still an open question. So we know the tower is there, we know the exponential rate. And knowing the exponential rate gives you information about what they should correspond to. So you can see that they correspond to, they have the same exponential rate than a Kaluza-Klein tower of different dimensions would have. But it would be nice then to follow to try to uncover the chain of dualities that make that manifest. That's open. Yeah, no, that's super interesting. Yeah, indeed.
Can you expand more on the non-critical strings? Are these supersymmetric theories? Do you know the full spectrum?
Yeah, so these are all superconformal field theories. So with n equals 1 or n equals 2 in 4 dimensions. And n equals 4. Like all the ones that have, what I show you here are the ones that have just one simple gauge factor. So there's just one gauge coupling and one limit to make it simple. And in some cases, like for instance, to give you one example, so one characteristic example of one of these theories that has one of these non-critical strings is n equals 2 super QCD with nf equals 2n flavors. Second? So in that case, I mentioned this example because in that case, there are very nice papers by Eli Pomoni, Leonardo Rastelli, and so on, in which they try to understand the bulk dual. And the critical string, the non-critical string, is a combination of, so you get both the fundamental string and also some DC branes becoming light at the same rate. So it's kind of a combination, like in the end what you get of these two, that are like non-critical. They also try to describe them as non-critical closed strings in a bulk which is not completely geometric. And there are some dimensions which are non-geometric. So this is one of the examples. The other one, I'm not sure yet. Like I'm trying to investigate better what should correspond to. But I don't have such a clear picture yet. But that's what we are trying to understand now. Okay, what are these? And especially we know where they should appear because of this exponential rate. So can we understand the bulk dual of any of them or connect them to each other? Yeah.
Yes, a more philosophical question. So when you say that you're finding constraints on quantum gravity, are these constraints do not seem to be based on general principles of physics, but more on specific predictions of string theory. So imagine, for example, let's imagine, for the sake of the argument, that the right theory of quantum gravity is loop quantum gravity. So are these constraints to be still true or not?
That's part of the program to understand, right? So here I focus on this, which really comes from string theory. It also has some arguments thinking of black hole physics now. So let me say, if it only comes from string theory, then we will always say that it's part of the string swampland. We don't know if it's a general feature of quantum gravity or not. The reason why we say, okay, we think there are constraints from quantum gravity is because sometimes you can give more general arguments independently of string theory. Like, for instance, the typical example is with no global symmetries. Like, you also have a lot of evidence from string theory, but you also have arguments just based on black hole physics that suggest that it's something more general. Whether it works in other approaches of quantum gravity, I think that has to be seen. Typically, it's not possible, like they are not explored so quantitatively to be able to check them. And I think, honestly, I think both options are fine. Either we realize that maybe they are completely general because they come from black hole physics and other more general principles that we think should apply generally, or maybe some of them are more specific to string theory and can help to distinguish string theory from other quantum gravity theories if they exist. So that's part of the program itself. And depending which one, there is more evidence for one or the other option.
One last question for Irene. I don't see any, so let's thank her again. Thank you very much.